This is your current balance apparatus. Let me bring it in closely right here. You've got two parallel wires. This one right here, this copper wire, is fixed to these posts on the end, so it's stationary. But then you'll notice that there's a wire parallel to that that's part of a loop, which is right here, and that's free to move. Okay. The circuit we've got consists of a power supply. Our current comes out of the power supply, goes into our ammeter. We're set to DC amps. It goes to this funny looking cylindrical device, which is called a rheostat. A rheostat is basically a variable resistor. So as this knob moves back and forth along this rail, it engages different segments of the wire and basically acts as a variable resistor. Right now I've got it set to fairly low resistance so that when the power supply is turned on, I should get fairly large currents. The currents in this experiment typically go from about 1 amp up to about 9 or 10 amps. After the current goes through the rheostat, it comes out here and goes into this little port right here. And you'll notice that there's two little rectangular pots here. And if I move in very closely to one of the pots, you'll notice that they're filled with a silvery material. That's the element gallium, and when I press down, you'll notice that the gallium is actually liquid. Gallium is an interesting element because its melting temperature is just a little bit above room temperature. So if you take a piece of gallium that's solid and hold it in your hand, it will actually start to melt. So these little heaters here guarantee that when they're turned on, they will keep the gallium liquefied. And so that way, as the little loop here oscillates up and down, those little prongs that go into the little pools of gallium always maintain electrical contact. So that guarantees that there's always current flowing through this top wire here. Now, we don't have to worry about this segment of the loop here. We just have to worry about the segment that's parallel to the stationary segment. The length of this movable segment is about 30 centimeters. And you'll notice that when I come down here, there's a very small gap between the wires. And when I measured it this morning, it was about 3.75 millimeters between their respective centers. And then you'll also notice that there's a little pan right at the top of the movable wire, and we're going to put on some mass there. Okay, now the masses that we put on are pretty small because this magnetic interaction is actually quite weak. So if I put on a 20 milligram mass, that's this. If I put it on the pan, that's a very light mass. That depresses the loop just a little bit. And when I turn on the current, we should be able to see the wires move apart. So let me hold this here and see if we can see this. So right now there's no current flowing. The weight has depressed the movable wire, so now it's in contact with the stationary wire. But when I increase the current, you should notice that top wire moving up. So that matches what we saw using the right-hand rule in the previous video. So the idea is that before I put the mass on, I measured the distance between the centers of the wires. Like I said, I measured about 3.75 millimeters. When I put the mass on, that decreases the distance. So then all I have to do is increase the current until I get back to that same distance. So I get the magnetic force of repulsion, pushing it back up, back to its original orientation. And then the goal of the lab is, as I vary the mass that I put on that little pan, I have to vary the current to get back to the original equilibrium position. And as you see in the write-up, if I plot the weight that I put on there versus the square of the current, I should get a nice straight line. If I fit that line, or fit that data to a straight line and figure out the slope, then the slope gives me a way to calculate mu sub 0, that quantity called the permeability of free space.